Okay, good morning, everybody. I'm Jay Meal, Chief Data Scientist and Director of AI, Algorithmic Warfare and Data Exploitation for SAIC. Happy to be here today to talk about operationalizing AI at the tactical edge. Despite the super cool and futuristic looking picture, I know we're not there yet. The joke about this picture is I asked AI to create what AI at the tactical edge might look like. And what I've learned from that is generative AI is seriously overestimating our capabilities at the tactical edge right now. I even asked it to let's make it a little bit more realistic, and that's what it came up with. Before it was robots and things like that. So, either there's a secret I'm not let in on, which is fine, or it's overestimated. So we're going to spend about 20 minutes delving into this topic around, really defining what is operationalized AI. And that's something we've spent a lot of time thinking about the past couple of years. We'll sort of define what does the tactical edge look like, what are the challenges around the tactical edge, and what are some mitigations to actually get real operationalized AI into place in DDIL environments, hardened environments, austere environments, whatever it might be. I will tell you this is not easy at all, and there's a lot that has to be done to get to this point, but I can tell you it's absolutely important for mission to be able to do this and to be able to deploy these models out into theater. Okay, so what do we mean by operationalized AI? A lot of people have a lot of different definitions. People like things in threes, so I've tried to break it down to three things. Operationalized AI means, number one, that you're going to reduce the cognitive load on the commander or the warfighter, and you're going to decrease task saturation using that through human-machine teaming. The second thing is increased speed to decision. So how fast can we get AI to help us make decisions and tip and cues so that we can look at a lot of things in the battle space? And the third piece is create a force multiplier. And what do I mean by create a force multiplier? I mean, using a human-machine team, machines are very good at things like finding patterns, finding a signal in the noise, alerting to different information, different entities, different targets, and giving that information to the human. And because of that, it allows the humans to look at more things or focus on other things. If your AI is not doing those three things, then there's probably no reason to spend the money to deploy it. So that's what we say operationalized AI needs to provide utility to the warfighter in whatever environment they're in. Okay, so let's talk about the tactical edge and sort of define the tactical edge, right? So that means geographic. So these are forward deployments, potentially in theater. We're talking technical limitations, limited connectivity, limited power, rugged conditions. We're talking about operational situations. This is about time-critical decision-making in disconnected environments. And we have to really account for things like size, weight, and power. We're not operating in a TOC fixed. We don't have data centers. We don't have large, HPC and computer processing. But we need models to be able to do the same sorts of things in those disconnected environments. And then this is sort of like focusing on those operational realities or those real challenges there, right? Those computational limitations. So very restricted processing power and memory, right? Data challenges, the inability to provide or have access to all of the data that you might need to train a model. One of the things I found in the 7 years I've been working in defense and intelligence is that our data sets are very sparse. We don't know what we don't know, right? We don't know if the enemy has particular signatures that we haven't been exposed to yet. We don't know if there's war reserve modes of capabilities. And so we need models to be able to generalize really well, which means we need really strong models that are operating and inferencing on really lightweight systems. And that's what I meant by this gets complicated. Communication constraints. As we discussed earlier, DDIL environments. Tactical edge is characterized by disconnected and intermittent and limited bandwidth. So this can present issues for AI models, especially when we're talking about edge nodes, where there might be multiple edge nodes in different systems that might not be able to communicate with each other. And how do we make sure models stay up to date? How do we make sure that we have a single source of truth? How do we make sure that we're getting the best inference possible? And then another thing is operational security, which is a real challenge. We have risk of model or data capture or interception by an enemy. We have risk of what we call adversarial machine learning, or the ability to poison data sets or to spoof data sets. or potentially even shift results inside those models. So how do we ensure the data that's being fed from the sensor into the model is truly the data that we expect it to be? It hasn't been tampered with somewhere in the transmission point, and we can ensure the fidelity of that data. So all of these challenges, including environmental factors and other limitations, seem pretty daunting, and that's why I said at the beginning we're not at the level of Dali's picture, and why this is actually pretty challenging. But it's not insurmountable, and that's really what we've been working towards at SAIC. We're getting very good at operationalizing AI in TOC fixed type environments or large platform type environments. We're doing work across all the service components, the combatant commands, and the national intelligence community with computer vision, natural language processing, large language models, and small language models, and Gen AI. But how do you bring that to the edge? And that's what we're going to talk about now. Now that we've outlined the challenges, we're going to sort of dive into strategies that we've developed to overcome them. So I'm going to just walk through these and talk a little bit more about what we're doing and how we're doing it, and then share with you the interface that we use to do this. And then I will open it up for questions, because I know we only have about 11 minutes left. So we can talk about this all day. We're trying to condense it, right? So again, now that we've outlined those challenges, we'll look at the strategies. And so the first thing we're going to look at is edge-optimized AI models. And so what do we mean by edge-optimized AI models? This is how do we make a model that might be heavy in terms of compute and processing more lightweight to operate on small form factor systems, right? Operate on a tactical laptop if it needs to. Maybe operate on a COCO platform with a particular sensor or device. And so what we have found is techniques like compressing neural networks is one example where we can make that work. So what's an example of compressing a neural network? I think probably everyone has seen like those representations of neural networks as giant trees with nodes on them. It's like pruning a tree. So it's being able to set up the neural network so that there's a way that it can sort of cut off its calculation once it's hit a certain confidence level, and it doesn't have to traverse the rest of that network. It's got a sort of like a bypass or an exit to be able to do that. That can decrease model sizes in some cases by 5 to 20 times in terms of compute and processing cost. Another thing that we're doing is quantizing models. And so what we mean by quantizing models is, I mean, let's be honest, AI is just math magic, right? So it is taking a lot of numbers and processing them, and quantized modeling is taking things like 32-bit numbers and shrinking them down to an 8-bit computation, for example, and then getting an inference on that. And what they found over time is you still get extremely high accuracy, but in a case of 32 to 8, you're speeding up your processing by 4 times. And so you can do that. So those are just some of the examples. The other things are ruggedized low power, right? So how do we ruggedize systems at the edge and make sure that we have enough power to do what we need to do on the inference side? And I'm not a hardware guy, so I won't focus on that. There's other people who are focusing on the hardware, but there's a lot of techniques and capabilities that are being done to do that. Back to the software side, though, let's talk about distributed learning for a second. So we talked about the multiple different edge nodes that might be out there, and different models are seeing different things at different times, and they might not be able to communicate back with each other. So how do we make sure that models can continue to learn, do continuous learning, or what we call federated learning, on each of those models, and when they are reconnected, they can all send that information, centralize back, and sort of reconcile, and then retrain. So that way, each model is learning independently of one another, and it doesn't have to be trained way back at, we'll call it like a TOC fixed, for example, or some type of command center. Another thing that I want to mention is robust communications, things like mesh networking. Being able to make sure you can transmit or prioritize and transmit how you're going to send messages that the AI might be inferencing on. So we're doing a lot of work now where once an AI infers something, we're actually using chain of thought learning with generative AI to say, what about this piece of inference or what about this message is important, and why is it important, and where should it be routed, and what's the best way for it to be routed? And all that can be done intelligently. So perhaps a fire's message is more important than another message. it can understand based on the payload and based on the metadata around the messages, and then make a determination of prioritization. It's actually something that we're doing in the intelligence community right now. And then finally, security measures. You know, encryption applied to data transmissions. You know, there's things out there where they're looking at privacy-enhancing technologies. There's capabilities like, you know, blockchain end-to-end from sensor to sensor to guarantee that the information coming off the sensor to the system hasn't been tampered with. And then training models on adversarial learning. That's a big one. So how can we better, I'll say, harden our models so that they know when they're being exposed to things that perhaps they shouldn't be exposed to? One way to do that is, I'll give you an example. We have a computer vision model that looks at satellite imagery of ships, for example. And sometimes those images can come in very distorted. Well, that would confuse a model. So if you wanted to be an adversary and you wanted to confuse that model, you could just sort of mess up the photos on transmission or something like that, intercept and mess them up. So you can do things like Gaussian blur, and you can actually harden the models so they can recognize more readily and easily the information that might be coming to them and need to be inferenced on without a perfectly pristine or pretty picture. You can do things like change orientation or size or rotate or add all sorts of noise to it to affect it, as well as have some, we'll call it some mitigation strategies in place in that transport side so that you're getting data quality and verification checks saying, is this sensor delivering me the right information? Is it in the format or schema that I thought it was supposed to be in? Is this the information that I was expecting before it infers and alerts the warfighter so that you're not getting bad information? So these are just some examples of these mitigation strategies. Before I sort of sum this up and open it up for questions, I'll say the one thing that's missing from here is the human element piece, right? So that's what we've been focused on at SAIC as well, is how do we deliver this to the warfighter? You have to imagine that if you're in an austere environment, a DDIL environment, you're downrange, you're probably in theater, you're probably in combat, and you're not going to be taking data scientists, data engineers, software engineers downrange into these fights. So how do we give the warfighters the capability to do everything that we just talked about? Fine-tune a model, you know, federate a model's retraining cycle, you know, get inference off of the model, adjust data sets as necessary. That's done in a no-code way. So we have developed an interface for the warfighter where it's all point and click, drag and drop, and they're able to actually infer and analyze and exploit data on their own with models that are built in and data systems that are built in, complete with a data flow that will give them a visual representation or a visual abstraction of what's happening. So you get a level of explainability, you get a level of traceability, and there's governance around each one of those inferences. So we're working today with you know, the Navy, the Marine Corps, and some of the combatant commands to actually put data science and put these capabilities, these AI/ML capabilities, in the hands of the warfighter, the mission owner, right, whoever they are. And we've actually found that the inference gets better, the models sometimes get better, and they're faster at learning these things because they understand the mission better than the data scientists, the data engineers, the software engineers, and they can apply it to their mission problems. So I would say, as hard as the challenges around the software are and the hardware are, and as hard as the challenges of getting the data right and training the models, that human element is the hardest. Not only getting someone to be able to operate it, but most importantly, trust what the models are giving them and build that cohesive human-machine team. And so a lot of that comes through that no-code data literacy and data science literacy and a lot of what we're doing on the AML side, as well as that traceability component. My background's national technical, and I did analysis, and I would have been so frustrated if a model told me this is your target and didn't tell me why or how it came to that decision. So being able to essentially invert and understand back to raw data how the system's making decisions increases the trust levels. Increasing the trust levels increases adoption, and then adopting it's going to help achieve the mission. So I'm going to leave it at that. I think there's about 4 minutes left for questions, but hopefully this was a pretty broad brush overview, this wide, this deep, on what we're doing for operationalizing AI at the edge.
So when you're talking about operational AI at the edge, are you talking about hot and fast data, or are you talking about cold and slow data in storage? And again, how are you going to be able to do that when Battlefield, when every time a connection from cloud, you're broadcasting your emission? Like, how do you command Battlefield commanders to turn on that models when they know the EMS is going to be there and they might be target for it?
So that's a great question. So there's a lot. So the question, in case anyone didn't hear it, was, it's really an LPI LPD question, right? It's how do we make sure that we're not, opening up a signal by receiving data from a downlink or something like that. Is that correct, sir? Okay. So I would argue that if we were truly in a DDIL environment, or at the farthest edge you could be, you're probably going from a sensor to a model. You may be connected to something. You may not actually be sending from a cloud downlink, or you may not be sending it, any other way that could be transmitted, right? Radio frequency, whatever it might be. There are techniques, which we won't talk about here, on how you can, spoof those things. That's out of the realm of AI/ML. That's more the data transport. But the idea is, if you are completely disconnected, how can I get data off of a system, even if it's by hand, and then do the compute on whatever system I have available to me? Does that help? Okay. Yes, sir. Oh.
On the same vein, have you considered smartly deploying mixtures of experts or mixtures of agents across the organization, so you can just manage that in the DDIL and then sync up while you can?
Yeah, so that's connected to that data mesh piece. So if you have multiple physical platforms, vehicles, whatever it might be, across different domains with different sensors and models running COCO, or different things running at an edge node, as soon as a network comes back online, you should be able to sync all of that up. And that's that federated learning piece. If you're talking about agents in terms of like AI agents, was that what you meant by agents? We're not really doing agents yet, because I think there's a lot on the explainability side that hasn't been understood about agents, especially on things like multi-agent learning and all that, that I think has a lot of people nervous. So what he's asking about is instead of building a model per se, having an AI system generate the best path or the best way to do something, and then having that sort of like propagate through different systems. That's that agent piece. But I think there's a lot to be, it's new technology. I think there's a lot to be understood still around how the agents work and how you control them.
My question is, what are the decisions what are the sensors sensing, and what decisions are being made for the warfighter? Is it like, hey, I'm being shot, would you like to call for fire, hit yes to send, or hit no? This is illegitimate data. Or is my sensors on the rifle and saying, hey, I need more ammo by this time based on where I'm at? What does that look like?
So the answer is, it's anything you want to set it up to do. But I would say right now it's more in terms of it's COA generation, right? So it's all about tipping and queuing. To me, where we get, as we potentially approach conflict, where we're going to actually get to with AI in conflict is course of action generation and tipping and queuing, right? It's letting the machines do what they do best, whether it's looking at satellite images for changes in movements of topology, or changes in movements of platforms, or keeping custody of multiple assets, or entity resolution against a maritime asset that says it's like there's 19 of them, but we know there's only one and we need to know exactly where it is. It's really about, again, taking that task saturation off the humans so they can go focus on the reasoning and the thinking and all of that. So it's all of the above, but I think it's really about the tipping and queuing and that course of action teaming. It's not going to be fully autonomous. And I would love to get to a point where the weapon systems can tell you when you're going to need a magazine refresh or something like that, and then let logistics folks know so it gets there before that's spent. But we're not there from a data perspective yet. The systems aren't interconnected enough. I mean, I heard, I was at a naval event last week. I was speaking there, and one of the admirals said that when we go into our next conflict, 80% of what we already have is what's going to go into that next conflict. So there's a lot of really cool things that can be done, but we're also dealing with platforms that are older, that weren't designed for AI/ML, that weren't designed to transmit data between system to system. And so we have to figure out integration points to make it smarter, but we're not going to solve all of those problems. So we have to figure out the best way and what we should concentrate on. And I really believe that's where let the computers do the thinking and the munging through all the data, right? The patterns, the needle in the haystack, whatever it might be, and let the humans do the strategy and the reasoning. And if you marry that up, I think we get a lot farther than we are today. Hopefully that answers your question. We may have time for one more. Okay. Thanks, everybody.